Good afternoon, everybody. Welcome to our webinar being put on today by Southern District of IT's Workforce Development Subcommittee of the Member Services Committee. That's a mouthful, I know. Today's webinar is the second in our series of webinars that are exploring artificial intelligence, or AI as we know it, as it applies to transportation. My name's Todd Brooks, and I'll be serving as the moderator for today's webinar. Let me cover a few of the obligatory announcements and housekeeping items before I introduce today's webinar and our speaker. Uh, if you haven't noticed, you probably were prompted when you logged in, but today's presentation is being recorded for later viewing. Um, I don't know that you have a choice, but please remain on mute until the end of the presentation, where there will be a time for questions and answers. If you think of questions during the webinar, what I would suggest you do is just drop those into the chat. I'll try to keep an eye on that. And as time permits at the end of the presentation, we'll get into the question and answer. We're working on the logistics of awarding PDHs, and that's still in process, so I don't have a great link for you now or way of recording your presence for that today. What I would ask that you do, and I dropped this in the chat as well, is send me an email at tbrooks@dewberry.com. And if you would like to get a PDH certificate, so if we were able to do that, send your name and your email address to me, and we will try to compile that and send that out after the meeting. And also, we always invite your suggestions and feedback concerning this webinar and any ideas for future webinars and training that you'd like to see. And we've got some upcoming, in addition to continuing the AI series webinars, we've got some others in the works on topics like mentoring and work-life balance and the life cycle of a planning project. So stay tuned, watch the Southern District SDITE connector for that. There will be announcements in that when those approach. And now I'd like to introduce today's presentation and our speaker. This webinar is entitled Smart Infrastructure Innovation in Chattanooga, Transforming Urban Mobility Through AI and Research. It will be an in-depth exploration of Chattanooga's groundbreaking smart infrastructure initiatives and the cutting-edge research driving them forward. This webinar will showcase how Tennessee's Scenic City is becoming a national leader in intelligent transportation solutions through strategic partnerships with the University of Tennessee at Chattanooga. We'll examine the innovative technologies being deployed, from connected sensors and IoT networks to advanced traffic management systems, and explore their real-world applications in creating safer and more efficient roadways. You'll learn how AI is being integrated with these smart infrastructure technologies to optimize traffic flow, reduce congestion, and enhance public safety. Our speaker today is Yasser Hassan, and I know you may have been expecting Austin Harris, but Austin unfortunately had an unexpected situation arise yesterday that prohibited him from presenting today, but he's arranged a highly qualified substitute presenter for us. Yasser is a software engineer at the Center for Urban Informatics and Progress at the University of Tennessee at Chattanooga, where he focuses on traffic optimization. He holds a BS degree in electrical and electronic engineering from the University of Khartoum. Did I say that right, Yasser? I'm not sure. Good. I
Yeah.
guessed right. His studies focused on electronic systems, software engineering. He has worked on the development and integration of back-end software and served as a middleware specialist. All that means he's a lot smarter than me, I think. He is Deputy Program Director for the Chattanooga Smart Corridor Project. So Yasser, we thank you for presenting to us today, and especially on such short notice. And I'll now turn the webinar over to you.
Thank you so much, Todd, for your introduction. And thank you for Southern District of IDEs to giving us the opportunity to present today and shedding the light on some of the work that we're doing as a collaborative environment between UTC, CUIP, City of Chattanooga, and our industry partners. I'll start by giving an overview of what is CUIP and how we started and our main pillars, which is like the Chattanooga Smart Corridor. With that, let's dive into the presentation. Second, okay. So CUIP is basically the smart city research center for UTC. It's part of UTC Research Institute. And the goal for CUIP since its initiation in 2018 was to strive for building a safer and smarter and healthier environment for city of Chattanooga. And this was aligning well with the city's initiative and goals. And we are focusing on the field of intelligent transportation systems, basically enhancing the city in terms of transportation through the application of AI and big data. Our main research areas that we're focusing in is the AI and ML and their application in the smart transportation area. And the subdivisions of the research areas that we're focusing on include, but not limited to, computer vision, sensor fusion, pedestrian safety, traffic signal optimization, connected vehicle to infrastructure, which short of CV2X and network CV2X, and ADAS, which short of advanced driver assistance system. So I think one of the main, like I would say, success pillars of our center is the collaboration, because we believe that collaboration is what's needed to build um, goals for larger entities. We're not just speaking here as center or like as university, we're speaking as a city. And with that in mind, you should enhance or improve your education and outreach, research and development, and real world deployments. And without a collaboration or like a robust collaboration between academia and government and industry, this can face a lot of complications. And this is what we do best here is the collaboration between the city of Chattanooga and our industry partners and our uh, the entities that provide the grants for us from USDITE, USDOE, and National Science Foundation. And I believe this aligns well with Chattanooga's vision, where our goal, like the goal is to drive economic development, workforce development, and most importantly, enhance the quality of life. And also the city of Chattanooga believe that the collaboration is the key, and that's why those goals overlap and align well toward our end goal for creating a healthier and safer environments. So let's start by talking about how we started as MLK Smart Corridor, and now we got the funds and the expansion for the full expansion to cover whole downtown Chattanooga with our Smart Corridor. From here, I think we're gonna dive a bit technical throughout the way, but I tried my best to not like be very technical and combine between high level and technical in this. So the MLK Smart Corridor started by covering those black intersections, which covered the MLK Boulevard. At each signalized intersection, the MLK Smart Corridor started by deploying a couple of sensors. We're talking about thermal cameras, CCTV cameras, 5 megapixels cameras, LiDARs, air quality sensors, edge compute nodes, and roadside units available for CV2X based research. And then with the fiber connectivity provided by the EPB, which are our utility companies, and the collaboration from the city in the deploying of those sensors and integrating with the UTC main data center, this was a seamless integration, I would say. And now the second phase of this, which already started, is the citywide research and development environment, or like the Chattanooga Smart Corridor, as we call it. This would cover 1 mile of highway and a total of 230 miles of urban road. This is covering all of the gray shaded areas, covering all downtown Chattanooga. That includes high density traffic areas, low density traffic areas, intersections, highways, and all of the different environments that would be helpful in our research. So what was the main drive that let us think about building this corridor? So basically, when you want to deploy AI-based solution, and especially in the transportation sense, uh, most of the solutions currently they utilize simulated environments because it's very hard for you to test your algorithms in the actual field, because um you would need some road closures, and those have to be planned ahead, and you would need a lot of planning in this area. So basically, this is what was the main drive. To deploy AI-based models, you would need data. So lack of data is the main issue for such algorithms to be deployed. Diversity of data, quality of data, and data analysis capabilities. And most importantly, the testing environment and the scalability. And this is what was the drive for this MLK Smart Corridor. The goal for it was to address urban challenges through data-driven research. And for the planning part that I was just talking about, the collaboration is the key for that, as we just mentioned. So this was the main goal for this development. So with the tons of sensors that I was just talking about at each intersection, and remember, with the full expansion, this will be at each intersection or at each pole. We would be having a couple of sensors. With the current 12, with just 12 signalized intersections, we're ingesting around 2.5 billion data points a day. So you would ask, how are we dealing with ingesting this data or doing our analysis? This is why we developed our Smart Corridor Plus, which is our cloud-based platform for managing this data. We developed what we call as Testbed as a Service. This is our cloud-based platform that provides streamlined access to the testbed resources and also to explore the different data types that we have and the documentation for how to access them. And we have also developed our software development kit, which available for users, for researchers to use. This SDK is basically ingesting the data or like giving access to the historical streams and real-time streams. You can see here, this is the login page for the cloud-based platform, and this is like how we are visualizing some of the sensory data. You can see here the air quality, you can see the traffic volume, and you can see also like some device management related data. So we have developed some sophisticated data pipeline. I love to include this diagram, which give you just a glimpse of how are we dealing with this data. So you can see here on this data ingestion module, we are getting the data from our different systems. So we're not just getting data from our sensors. We're also getting data from the city provided sensor, like the Grid Smart system, which currently is being used to actuate the traffic signals. And also we're getting like the data from video analytics throughout CCTV cameras and the LiDARs. We are using a sophisticated message event distributing systems to ingest the data both into like index database where we can query the data for analysis, and also we are ingesting the data and letting them land in a data lake available for historical access. Our second module is data monitoring and alerting, because of course, with this tons of sensors, you would need to be proactive in like maintaining those sensors. So getting alerts whenever a sensor fails is crucial. And this is what we're doing here, is that we are providing a robust data monitoring and alerting pipeline that gives you an alert whenever there is an issue with a sensor or with data, and so that you can be proactive in maintaining them. And the last module, which is most importantly, the user access module, we are providing access to our data, our different sensory data throughout installable SDK that uses Python-based libraries, and also through public REST API that you can call through your code or like through your scripts, so that you can utilize our data. And let's dive a bit deeper into the facilities, more than just like so yes, the smart corridor is the main pillar, but there are like other facilities that helping this, integrating the whole scenario for making the test bed a living real world testing environment. Our main buildings are the MDRB and the EDNI. Those host, like the MDRB hosts our main data center, which contains like more than 3,000 cores and 4 terabytes of GPU in total that is available for research. The EDNI building contains our main traffic management controller or traffic management center, where we are visualizing the data and where we can see and monitor the status of our sensors or like the current traffic. All are integrated in one place, what we call it the TMC. You can see our simulator. This is a facility ready to use for testing autonomous vehicle-based research, for example, where you can test your algorithms here first before you taking them out in the field. This traffic box is what will you see at each intersection in downtown Chattanooga, where we are deploying our edge compute node, and where the city installs their traffic controllers that actually controls the traffic signals. So basically, we have this one here so that we can test through what we call hardware in the loop and testing our algorithms first in the lab before getting them out in the field. And finally, we have a test track available for either electric vehicles research or autonomous vehicle research, which is like it's used to be a TDOT, but now it's a collaboration between Tennessee Department of Transportation and UTC and available for research. Those are some of our industry partners that are helping us uh, in deploying some of the sensors that we were just talking about, like the LiDARs, RSUs, and other sensory data. This in addition to our government partner that includes National Science Foundation, USDOT, USDOE, and most importantly, State of Chattanooga through its different parties. So now let's have a deeper dive on some of the real world projects that we are trying to solve. One of the main projects that we got the grant for from the FHWA, Federal Highway Administration, is the Advanced Artificial Intelligence Research for Equitable Safety of Vulnerable Road Users. The product scope for this project is to develop a cloud-based automated processing pipeline that includes the data annotation, model training to be able to detect users. And the second part of it was multi-sensor fusion framework. And this is basically to track objects, what we call it road users, and then being able to fuse the data from different sensors, say, for example, camera, LiDAR, and thermal camera. And so the goal for this was to have the most robust trajectory that combine the data that is missing from different sensors and utilize the power of each sensor to have one robust trajectory. And the final goal, or like the final module of this project, was to develop an AI-based safety engine that is available or that is able to provide some risk assessment and near-miss identification for the scene under study. This project is currently under development, and it's a collaboration between the University of Arizona, University of Tennessee at Chattanooga, and University of San Francisco. I love to show some videos that reflect the different parts of the projects. So for example, for the first part of it, which is the data annotation, model training, and tracking, you can see here on this video where we train AI-based models that is capable not just of detecting or tracking a car, but basically there are some models that we can retrain, and we retrain that is capable of identifying the make and model of the object itself, of the car itself. And here you can see the second phase of the project, which is sensor fusion, where like you can see the red and the blue dot. I'm not sure if you can see them, but those are fusing data of objects from camera and LiDAR. Sometimes the camera cannot detect, LiDAR can be integrated, and you can have a full trajectory. And here, this is this video summarizes some of the work done on the last step of the project, which is the risk assessment and near miss detection. Basically, for scene analysis, in this sense, you would use measures like time to collision, post-encroachment time, which we call it PET. Those are used combined with trajectory prediction of each object so that you can identify if this intersection has a high risk score, or if there is an alert about maybe an upcoming accident, so you can get some alerts. So for example, you can see we do trajectory prediction for two bounding boxes, and we calculate time to collision between those IDs, which represent two different objects. And this would tell you like there's a 3-second time to collision, for example, and you can set some thresholds that can trigger some alerts. Another project is about digital twin and simulator. This is another project which was a collaboration between different universities, University of Tennessee at Chattanooga, Georgia Tech, and University of Pittsburgh, Oak Ridge National Laboratory, and City of Chattanooga. They helped in building a simulated environment for the MLK Smart Corridor. Basically, you can see here we are integrating the SPAD data, signal phasing and timing data from the traffic controller, along with the traffic volume data that we're getting from our different sensory data. And you can see like the red detector shows like red traffic signal. And this simulated environment is helpful for training data in simulated environment, for example. And also this data can be exported in certain formats and be used in our simulator, for example. And this is basically what we did. And what you can see here in the driving simulator, where on this video, you can see here in the simulator, you are driving through Georgia intersection, and this is Georgia intersection. So this is basically built through different tools. Some of them is FISM, as most of you may know about it, Roadrunner, and we are exporting this into our simulator so that we can mimic the actual real-world environment and test our AV-based or any other type of research on the simulator. Another project is traffic signal optimization. This was one of the most interesting project that we got the chance to test it out in the field, basically. And the goal for this project was to improve the corridor level fuel consumption and reduce the emissions by reducing, like, for example, the stop and go percentage. And in very simple terms and in very simple words, this basically, instead of having a fixed time for the traffic signals, you want it to be adaptive and to be coordinated throughout the corridor. And for this project, we used reinforcement-based reinforcement learning-based algorithm which was trained on a combination of a simulated data from the digital twin that we've built, and also a real-world data for this model to have the best combination of variables for each intersection. And this data is then can be used for this data actually used for having the best set of parameters that can be used to tweak the model and change the traffic signal. You can see here on this video, this is the actuated, which is currently running the intersection through Grid Smart System. And this is the DG-MARL, which is our reinforcement-based algorithm. And you can see, like, for example, here, it's always green, or like it tries to maximize the green time, where here it stopped on this red arrow. And basically, at the end of the day, you still have to comply with the rules of traffic signals, like minimum green time and minimum red time, which was like basically rules that you have to follow. It cannot be adaptive all the way, if that makes sense. This is another video shows that we are testing this. There's a simulation environment where we test the algorithm in the simulated environment first. And then the final stage for this project was we tested this in 6 intersections in the MLK Smart Corridor, where we controlled the traffic lights in real time. And we saw a reduction on this ACOPI, which is the measure that specifies if we are improving the energy the fuel level consumption or not. Another project is about the connected vehicle to infrastructure. And we have 2 projects in this area currently ongoing. The first one is cooperative perception. So CV2X is it's basically like the protocols that connected vehicle can communicate with the infrastructure and send the data so that this data can either be shared to other road users that are not connected or can be utilized for analytics research, transportation related research. This project basically uh, it's utilizing the data from other sensors. Like for example, if you have a LiDAR that is providing the traffic volume, um, you want this data to be available for other road users so that they can know about, for example, there's a pedestrian crossing, or like vehicles can communicate together even though they're not connected. One of the projects that we're currently working on, we are working on an application that is installable at each mobile. And this application can be in anyone's mobile that you can download. And this application utilizes the data from our roadside unit, which gets the data through certain protocol called SDSM, getting data from other sensors. Let the user know based on its current GPS location um, that there is a pedestrian, for example, or that there's a certain alert that the road user has to know about. Another project in this area is transit signal priority and emergency vehicle preemption. Basically, the emergency vehicle preemption can be equipped with an onboard unit that can communicate with the roadside unit, and an action should be taken at the traffic controller level, changing the traffic signal to green, and let the emergency vehicle go and preempt the street. Another projects in the pedestrian safety, which is like I really like talking about this project because it basically reflects the actual impact that we are trying to make, or like the actual issues that we're trying to solve. So basically, the UTC campus, they identified areas of concern for pedestrian safety. Those red dotted circles are like some locations across the campus, including mid-block and signalized intersections. They wanted a study about like one of those locations. It has a high percentage of jaywalkers just by looking, but they actually needed an actual verified data analysis so that they can make decisions based on that. And I would like here to talk about our mobile data collection unit, which will benefit in this project, which benefited in this project actually. This mobile unit is available to use at each intersection, or like at each area that there is no uh, sensors, or like it's not convenient to install sensors at. It runs using solar panels. It can work for multiple days. And at each, the sensors that we have is thermal camera and CCTV camera and a LiDAR. We utilize this mobile unit to install on one of the locations. Basically, we did some analysis to study the amount of jaywalkers on the mid-block crossing. We found, so basically the scenario here is that there are like two traffic signals, or like there are two crosswalks. They're a bit far from each other. So pedestrians find it a bit long walk to walk to the other and crosswalk. So they just do mid-block crossing, even though there's no crosswalk at that spot. So we did study that, and we found there's like 518 mid-block crossings with like 207 near miss incident with 5-second post-encroachment time, and 33 with 2-second post-encroachment near miss incidents. So basically, we provided the campus with this data through a communication with the city. A temporary crosswalk was put in the middle between those two crosswalks, and we did the analysis one more time. We found 0 near miss incidents with the new temporary crosswalk being put, and there was just like 33 out of mid-blocks crossings, and you can see the huge reduction that happened here. I think I was just trying to shed the light on some of the projects we're doing. We're doing much more than that, and those projects can dive very deeper in the technical wise of it. But I was trying to be uh, somewhat high level when reflecting those. And with that, I conclude the slides that I was talking about, and I'm happy to answer some of your questions.
Yes, sir. Thank you so much. Excuse me. Sorry about that. Thank you so much for your presentation there. We do have time, plenty of time for questions. You can either, excuse me a second. You can either put that in the chat or I don't know if I'd be skilled enough to allow you to come off mute. I may try that. If you've got one, if you raise your hand, I can probably do that. I have a couple of questions I'll ask if not. There's one. Dante, let's see. Allow you to talk. I don't know if you can or not.
Can you hear me?
Yeah.
Fantastic. Hi, my name is Dante Gutierrez. I'm with the city of Greenville, South Carolina. Regarding the component of machine learning and artificial intelligence, I did notice that the main use was more so for identifying vehicles and identifying and categorizing the different users of the road. But one application that I've been interested in for the purpose of this type of models is to be able to analyze different factors that would normally be a little less tangible for us as traffic engineers to help us optimize signal timings. For example, we have some locations down here in Greenville that, due to the elevation changes, I've noticed that startup loss time, right, is larger than some other locations. That being a combination, of course, of the geometry of the intersection, elevations, and of course the type of users that normally drive that road. When I think of machine learning and AI models, I think more of it in terms of how can we utilize this big data type of technology to really help us refine all of these factors that historically really just require us as engineers to just make some base assumptions, base numbers, because from an operational standpoint, one of the biggest challenges that I've seen when dealing with peak time travel times and peak time timings is how can we maximize the usage of our green time, right? That we have allotted for any given time period as we go through different locations. So, if possible, if you could maybe shed some light as to how some of these technologies, right, can be utilized to help us really like dig deep into not just the overall type of vehicles, but all of these very nitty-gritty things that historically would require us to perform, long-standing studies, right? Several days of observation and data collection into something that could much more easily synthesize to really enhance that ability to do travel time and split determination and adjustments.
This is a very good question, and I think to your point, one of the projects that I talked about, which is the adaptive traffic controlling system, it was basically developed through what we call it reinforcement learning based models, and basically the idea is that it tries to study the embedded kind of features or parameters that we cannot dig into each one of it. Like for example, user behavior, like the road geometry as he was just talking about. So basically, some of those, if they are very hard to be gotten, you could use the model to with different seasons, which actually what we used, we tried to use training data from different days, from different month, and even from different seasons, like in winter versus in summer. And this data can give you implicitly the sense of the hidden parameters that you're just talking about. And I was just in a meeting with another company. It's called, I believe, Placer or like .ai. They provide different type of data related to the location of the user. And this type of data, for example, I just knew about it, can be embedded on our models to study the behavior of the user after, let's say, changing a design in a road, for example. One of the other projects that we worked on is the redesignation of Fraser Avenue in downtown Chattanooga. So basically, we could use such another user behavior data to study how, if this redesign actually benefited the road or not, in the sense of how did it influence the business, travel times, and other factors, as you was just mentioning. So basically, to your point, I believe, yes, those parameters you were just talking about are very valuable in machine learning models. But when you don't have, or when it's very hard to get such factors, deep learning models, through a lot of data provided and in different, more generalized seasons and areas, can help in identifying implicitly the factors that you're just talking about. I hope this partially answered your question.
It does. Thank you.
Yeah.
Yeah, I have some experience with adaptive systems as well. And, historically, they don't do so well when we're talking about saturated conditions because they basically function almost like a pre-time system. For me, when it comes to adaptive systems, I'm more interested in how they allow the signals to behave during those shoulder times, approaching clearing the peak. Because from a traffic operational standpoint, I understand that sometimes during peak saturation, you can't really optimize, your way out of it just because everything is maxing out, but allowing the recovery to improve and enhance in order to clear those built up latent demand queues faster is where the real benefit of this type of systems comes into play. So, do you have any other thoughts on that as well?
One of the features that we are utilizing on the adaptive traffic controlling system that we're using is basically, we're taking into consideration the occupancy and the traffic volume, and basically the carried information from different intersection, like from successive intersections, from this to that. So those kind of information helps in uh, when you are embedding such information like the occupancy. Basically, it means you are trying to optimize for that exact parameter, like the occupancy, which is the length of the line, as you definitely know. So those kind of parameters can be like, an iterative process of optimizing. So I believe the more parameters you're embedding to the model, the more optimization you will get for increasing or maximizing the green time and minimizing the red time.
Thank you.
There's another question. I saw it on the chat, which is
Yes.
yeah,
Yeah.
UTC looking at quantum computing being utilized. Basically, the other pillar of UTC Research Institute is the quantum lab, or the quantum center. And one of the major research that they just started digging into is basically how can we use the quantum computing in our real world deployments, because at the end of the day, having installing a lot of powerful edge devices at each intersection might be not feasible at each intersection. So this is one of the researchers this center is currently working at.
And yeah, sir, I do see in the Q&A session too, there is one there that says, I can read it. Is there any other big data that you are incorporating into your program from companies like Google, such as Heartbreaking, et cetera?
So basically we have, like, for example, our LiDAR system is being provided by Ouster. So Ouster is a company that provides the LiDARs, install them, and also they have their own software that is capable of providing event messages regarding trajectories of road users. That includes uh, cyclists, vehicles, pedestrians, and this data comes in like 10 hertz frequency, so you can tell like how big this data is at each day. So and also like we have uh access to the grid smart data and the traffic controller data, which is signal phasing and timing. We are ingesting the data not just from our sensors, but basically from many third parties. Uh, the ones that I just mentioned are just like some of them. And we are dealing with companies like AWS for um, our cloud storage. And we are always looking for collaboration in the sense of either having access to data or a collaborative project that benefits the society.
Thanks. There is another one that's popped in too. Question is, with such a big technology advancement in this area, is there any infrastructure or programs you would recommend to assist in preparing for the future so that owners can keep up with technology?
So this is what I like about LLMs, which is basically like tools like ChatGPT. Um, the utilization of such tools would be beneficial as a starting point in directing people into either resources or either high-level explanation of a complicated term, uh, help directing you. But what I always advise people with is that not relying 100% on those tools, but basically relying on them for a starting point and let them provide you with citations and references that can take you to a certain link, and then you can verify the information yourself. This would, this for me personally, helped me a lot in reading papers, inspecting new technologies on certain areas. And then you can like, it can uh, suggest a course, for example, that you can go and learn about. This, in addition to the blog sites, for example, like Medium, where like people provide some articles about some hot topic, state of the art models that you can utilize in your research. So basically, yeah, there are a lot of tools that can help in being updated with the I would say market, or like with the technologies.
Looking to see, there might be a, yeah, Dante added something in here. Just to add to the topic of generative AI models, there are some issues regarding these types of models, quote unquote, hallucinating, as well as outputs being inadvertently affected by bias in the input.
I totally agree with that, and that's why I said like you should not rely 100% on those type of models, but those type of tools help you summarize. For example, for me, sometimes I find it very difficult to read a whole like uh, book, for example, and I would say, or like a whole article. So sometimes having summarized the article that you need, and then giving you a guide on which links to follow, and then you can by yourself then verify and take yourself from link to another link, or like from video to a course to a blog post, and yeah, so you should not like rely 100% on that, because as Dante mentioned, the hallucination is real in those type of models.
Thanks, Yasser. Anyone else got questions? You can certainly pop them in the Q&A or type them in there or raise your hand. I'll pause for a minute just to give anybody else an opportunity. Yeah, sir, I did have some that are, I'm not, mine aren't as deep as some of these other questions. Mine are more basic about some of the hardware and infrastructure that you've got. You mentioned towards the end there about the mid-block pedestrian crossing. We end up doing a lot of those. So did, did you, when y'all installed the mid-block crossing, did it have any other, was it just markings and signs, or did y'all have any other devices there at the mid-block crossing? anything like an RFB or anything like that?
So basically, the what we had is sorry, what we did is basically you can see the mobile unit has been installed, and this was just the only uh, device that we used to collect the data that we needed. Um,
Okay.
it actually counted the amount of road users across this temporary put crosswalk, and at the end of the day, it just like generated a CSV file or a heat map as the one that you're just seeing, and based on that, we just made the decision um, of having putting the crosswalk, and it was just the crosswalk and a sign, and nothing else has been put out there.
Thank you. I appreciate that. Another one I had was your C to VX discussion there.
Yeah.
Are y'all using just DSRC communications and with onboard units and roadside units, or y'all using any kind of cellular-based um, technology?
We're using both. We're using cellular and we're using DSRC. Um, Basically, there's a nice graph that uh, let me just stop and I will share in a second. It's a slide that I'd love to share that summarizes the different communication mediums and protocols that we use. Second. So basically, if you can see on this diagram, those are like different type of communications like DSRC, 5G, Ethernet, Wi-Fi, and Bluetooth. Those are all supported types for the CV2X.
Very good, thanks.
Mm.
Um, Looking to see if we have any more questions. I don't see any off the head. Don't see any raised hands. Nope, don't think so. All right. Well, yes, sir. We definitely appreciate you sharing this information. Very interesting project. I'll have to get out to Chattanooga and take a look firsthand. I was out there about a year ago and didn't realize all that was going on. So, shame on me. But if I get out that way again, I'll have to take a look.
You really
Uh,
have We'll be really excited to have you here.
yeah, yeah. Well, it's. I've been out there a couple times. Beautiful city, and so definitely got another reason to try to get out there. Um, just to recap, everybody. First of all, again, thank you, Yasser, for doing that for us, especially on short notice, and just to give some follow up comments, if I can find where I wrote them, um, to keep me straight. Um, we hope this webinar has been something that enhanced your understanding of AI and transportation, how it applies, and then particularly this project at the Chattanooga Smart Corridor. Um, we did record this. It'll probably be made available if you wanted to re-listen to it. We usually publish that in the SDITE, the Southern District online electronic newsletter. It comes out once per month. We'll probably publish a link there for those of you who may want to see that again. Um, we'll have future webinars, as I mentioned. We announce those through the SDITE connector. If you're not an SDITE member and would like to know how to receive communications about that, you can just drop me a line, let me know, put something in the comments section, or send me an email, which I provided in the chat. And regarding, again, I've had at least one email come through already requesting PDHs. You can send me the email, as I said earlier, or you can drop it in the chat. You can self-report and not get a certificate, whatever works best for you. But certainly we'll try. Sorry for not having all that completely arranged beforehand, but we'll try to get that taken care of very quickly after the webinar. And with that, we'll call this a close to this, and we thank everyone for attending today, and look forward to our future webinars. Have a great day, everybody.